Hey everybody, thanks for joining me. We are on the third in the series of ionic compounds. And now we're at the point of looking at electrolytes. So this is that word that always makes us think of Gatorade. What makes it an electrolyte? So we have done this definition before, so let's do it again. An electrolyte is a solution capable of conducting electricity due to mobile charged particles. Okay, so mobile means the particles can move, and charged means they're either positive or negative. So if you have a solution and it's got positive and negative moving particles, it can actually conduct electricity. So if you haven't seen it yet, I have a really cool demo that I'll show you in the class. We'll use some Gatorade, we'll use some different solutions, and we'll see which ones can light up a light bulb. And if they can light up that light bulb, they've got mobile charged particles. We know that some things, metals, are able to conduct electricity as a solid. That's not an electrolyte, that's just a solid. That's not a solution. It is simply a solid that also has mobile charged particles. So the little electrons within a metal are like a sea of constantly passing their electrons back and forth to each other. That's a little different because it's not a liquid and it's not something dissolved in water. All right, so water is a covalent molecule, but it does have slight charges. So we've been talking about ionics and the charges they have and the positive metals and the negative nonmetals because of that transfer of electrons. But now we're going to talk about water. Like, what does water have to do with any of this? So water is covalent, meaning it has no metals in it. It is simply made up of non-metal atoms, but the oxygen is slightly negative and the hydrogen is slightly positive. And so we're going to draw it. So here is our O, and here is a bond to the H and a bond to the H. So there's my atom, and there's my atom. And then this is going to have a little negative on it, and these are each going to have a little positive on it. Now, there is no transfer of electrons, none whatsoever. This bond, this covalent bond, is actually showing that they are sharing electrons. So when there's no transfer, there's no ions. So these do not form ions, but they do have very slight charges to them. All right, water is very cohesive. So that means that water is attracted to each other. I'm going to write attracted to itself because one water is attracted to another water, and it holds itself together. If you've ever taken a drop of water and spilled it on your desk, which I'm sure you have, or spilled it on your kitchen table, the water will bead up, and that's because the water is attracted to each other. So unlike, let's see if did you ever spill like nail polish remover? If you spill nail polish remover, it really spreads out quickly and it evaporates quickly. But water isn't like that. Water really attracts to each other and comes together and forms little beads of water. It stays together. So now it tells us to draw another water molecule above and draw a dotted line to show the strong attractions. These are called hydrogen bonds. Okay, so I'm going to draw another water. I'm actually going to make it another color. This H has a slight positive, so I know it would be attracted to a slight negative. So I'm going to make my O be right here. So there's my oxygen atom. And I'm going to make my H be right here, and my other H be right here. So the H's have slight positives, the O's have slight negatives. And then I'm going to take another color and I'm going to show, there's the attraction, there's the attraction. So that attraction, that's the hydrogen bond. Excuse me. All right. Why do you think ionic compounds are able to dissolve in water. So pause me for a second and fill in your answer right there. All right, what did you put? I'm hoping you put something about charge, because ionic compounds we know are made up of ions, and ions are charged particles. So those ions are going to be attracted to water's positive and negatives. So I wrote here, ionic compounds dissociate into ions when placed in water. Then these ions attract to either the hydrogen or the oxygen atoms of the water. When this happens, spheres of hydration form. Draw the ions, and spheres of hydration then form when NaCl dissolves in water. Okay. Here's Na, it's a plus. Here's Cl, it's a minus. How do I know that right off the bat? First of all, Na is the metal. Metals always lose their electrons. I like to call them left side losers. I don't know if I've told you that or not. Left side of the periodic table tends to lose electrons, so left side losers. When you lose a negative, you become positive. You can look up in the top right corner of Na's box on the periodic table, and it's a +1. Cl is a nonmetal. It's on the right side of the periodic table. They tend to gain electrons. If you gain a negative, you become more negative. So you look up in the top right corner of Cl, and it's a -1. Okay, so now I need to draw my waters. So I'm going to go back to red. The H side was positive. The O side was negative. So I'm going to draw, let's say, 4 waters around this sodium. The O's are going to face it because they're negative, and the H's, which are positive, are going to be away from it. Okay, so here is my sphere of hydration. I'll show it in this gray here. That's my little sphere, and it's all these attractions that hold it together. And then over here on the Cl side, I need to show all these H's surrounding the Cl. Like that. So on this side, here's my sphere of hydration around the Cl. And all these pluses are attracted to the negative of the Cl. So isn't that cool? That's what a sphere of hydration is. I like to think of it as like if I had a handful of salt in my hand, it's the bright white crystal. I see the crystal structure. I know it's ionic. And then I throw it into water. And all of a sudden, when I throw it in water, it's like it's disappearing. And what's happening are the little Na ions and Cl ions are separating from each other and getting surrounded by water. And the pluses are going to get subtracted, or they're going to get attracted to the negatives of oxygen. So oxygens are going to go around it in a circle. And then the Cl is negative. So any negative ions are going to get surrounded by the positive H's of water. And that is called a sphere of hydration. And I've got mobile charged particles now. So because I have these mobile charged particles, I'm going to be able to conduct electricity. So the ability to conduct electricity is based on the presence of mobile charged particles. They can now move. This is moving and this is moving. Before, when it was in my hand, it was a solid. It was not able to conduct electricity because it was not moving. But now that those ions can move, it can conduct. So let's draw little pictures. If I have solid NaCl, remember I get that crystal lattice look? I'll draw them so that they look like separate compounds, but remember they're super close to each other because of the attractions. So that's what it looks like as a solid, and it cannot attract or it cannot conduct electricity because these particles aren't moving. I do have pluses and minuses, but they're not freely moving about. If I have a solid, they might be vibrating back and forth, but they are not freely moving around. If I melted it, so if I was able to melt a salt, first of all, it would have to get crazy hot. But now I would start breaking the attractions. So now my salt molecules have moved apart from each other. I can sort of draw them all over the place here. And now, because they are freely moving, so I'm just going to show little arrows of motion, and this is a plus, and this is a minus, and a plus and a minus all over. Now, these can conduct electricity because they are mobile. I know they're charged. They were charged before, but they weren't mobile before. And then if I have them dissolved in water, all right, if I have them dissolved in water, my Na, my plus, gets separated from my Cl, which is my minus, and it gets surrounded by water like this. And it forms those spheres of hydration. So first I like to draw the water. Then I'll just put all those little teeny tiny pluses on the H's and little tiny negatives on the O's. That's a sphere of hydration. And over here, this is going to get surrounded as well. Little negatives on the O's, little positives on the H's. And those are my spheres of hydration. So can it conduct electricity? Yes, absolutely, because again, they're mobile. If they can move, then they can conduct. But when they were a solid, they just weren't able to move around. All right, last part of our Ionic series of videos is about electrolysis. So electrolysis happens in an electrolytic cell, let's start off with this. Ionic compounds dissociate in water, but this is only a physical change. How can you get the ionic salt back out of the water? So hopefully you're telling me right now, if I took salt, if I took salt, threw it in a glass of water, mixed it up, it looked all dissolved, you can't even see the white anymore. How could I get the salt back? I would have to evaporate the water away. And by evaporation, that physical process removes the water and restores the salt. And when you do this, are the properties of the salt still the same? Yes. Salt has the same properties in both conditions, both in my hand as salt and in the water as salt. You can think about tasting it. I know we usually don't taste anything in the lab, but when I use table salt as an example, that salt flavor, whether it's in a solid form or dissolved in water, is the exact same. So physical changes do not alter their properties, but the bonds are still present, meaning NaCl is still an ionic compound because of its ionic bond. I have not broken the bond when I dissolve. So breaking the bonds in an ionic compound to form the metal and the non-metal ions is a non-spontaneous. Non-spontaneous means it does not happen all by itself. It is a reaction that requires the input of energy. You can't do it all on your own. You got to add energy to it to make it happen. So let's think about our table salt, our NaCl. Again, it's an ionic compound made from sodium metal and toxic chlorine gas. Are these properties retained when the salt forms? Heck to the no. No way, because we eat salt. And so salt is neither a metal nor a toxic gas when we eat it. It has all new properties when it forms its compounds. We know salt dissolves well in water, and when it dissolves, the ions are surrounded by those spheres of hydration. Oh, of was already written for me. Spheres of hydration. And since there's mobile charged particles, the solution is an electrolyte. Probably never thought so much about salt water in your life, huh? Chemistry is so cool. All right, when the NaCl is dissolved, it's still a compound. The bonds are not broken. To break the bond in 1 mole of salt, you would need 787 kilojoules of energy. So we are going to actually do this in lab. So we are going to do this today in our lab room. We're going to break a bond between the ions in an ionic compound, and we're going to separate the metal and the nonmetal atoms that make up the compound. To do this, we're going to use a battery as a source of energy. And scientists discovered the 2 electrodes that a battery has to attract the ions and move the electrons from one to the other using a wire. So we are going to do this together, and we're going to draw it out. So first, we are going to have our solution. Let's just use salt again. So if I actually wanted, I'm going to write that it's AQ right now. Okay, so AQ means aqueous, which means it's dissolved in water. So that's my solution. I'm going to have a battery out here. Batteries have little electrodes. One of them is going to be positive and one of them is going to be negative. When you have a battery, the negative electrode is the cathode and the positive one is the anode. All right. I then need to have 2 electrodes. Electrodes are my anodes and my cathodes. And in our lab, we're going to actually use pencils. And so we sharpen the pencils so that the graphite is sticking out like this. And then we take some alligator clips. And so we clip this on and we clip this on, and it's connected to a wire, and we clip it onto here. And this is connected to a wire, and we clip it onto here. So you know those little alligator clips, you pinch them, you attach them, which means that positive charge goes all the way over to here and over to here, and the negative charge goes all the way over to here and all the way down to here. Okay, so let's think about our reaction that is happening first of all, and let's draw that out. Okay, so NaCl. NaCl is going to break down into its elements. So Na is an element and Cl is an element. But I know as soon as I write that Cl, you guys are thinking like, wait. I know something about chlorine. Chlorine is diatomic. Yes, it is. So that means I got to put a 2 there because chlorine is never by itself. So if I separate the chlorine from sodium, it's going to have to bond to another chlorine. And so to balance that out, if I need 2 Cl's here, I'm going to have to start with 2 NaCl's, which means I will make 2 NAs and then the Cl2. And now everything is balanced. I have 2 NAs at the start, 2 NAs at the end, 2 Cl's at the start, and 2 Cl's at the end. Okay, now when this is by itself, it's not going to have a charge anymore. And when this is by itself, it's not going to have a charge anymore because it's an atom. It's not an ion. But over here, when it's an ionic compound, Na is a +1 and Cl is a -1. So those Na +1s are going to be attracted to the anode. All right, no, I'm sorry, to the cathode. Why would they be attracted to the anode? The anode's positive. I want to attract them right here to this minus. So I'm going to write Na plus is going to go right here. It's going to go right to this end. And then Cl minus is going to be attracted right here to this end. All right, and then I'm going to write what are called half reactions. Okay, so we've never done this before. We have 2 kinds of reactions. We have oxidation reactions. That's the one that loses electrons. Oxidation always happens at the anode. And then we have reduction reactions, and those always happen at the cathode. I like to say anox and red cat. That's always how it happens. And this one's going to gain electrons. Okay, so at the anode, we have this Cl minus. So I'm going to start off with the 2 Cl minus 1 ions. So up here, 2 Cl minus 1s. they are going to lose electrons, and they're going to form what's over here, Cl2. So first thing I want you to notice, 2 chlorines, 2 chlorines. That is balanced. But they also have to lose electrons, and we're going to figure out how. If this goes from a -1 down to a 0, that's a change of 1. And I have 2 chlorines doing it, so 2 times a change of 1, that's 2 electrons they would lose. Each Cl right here that goes to this is going to lose an electron through the wire. So electrons, and I'm going to have 2 of these, which means I'm going to have 2 of these, which means electrons are going to go through here. When I form this Cl2, these are my bubbles of chlorine gas. They're going to actually bubble right out into the air, and you can literally smell it like a pool. The electrons go through the wire, and so they're pulled away from chlorine, and they're pulled to this battery, and they go through over to this side. So every time I have, we call these redox reactions. Every time I have a redox reactions, the electrons that are lost at the anode are going to be gained at the cathode when I have a battery. So over here, my 2 NAs with a +1 charge are going to gain electrons through that wire, and they're going to form, here's my end result, 2 NAs. So if I have 2 NAs on this side and 2 NAs on that side, that's balanced. And now I have 2 +1s, and I have nothing over here. So I'm going to have to add 2 negatives to balance that out. So each Na will gain a negative electron to become just sodium metal. And the sodium metal is going to form atoms that are going to clump all around this cathode. So the cathode is going to actually gain mass. I like to say the red cat gets fat. It's actually going to gain mass on this side as the metal forms. So my reaction broke salt into sodium and chlorine gas. It did that by attracting the ions to their opposite electrode. So the positive went to the negative went to the positive. My electrons went through the wire from where they were lost here at the anode to where they are gained here at the cathode to form atoms. So I now have sodium atoms and I have chlorine atoms. And so that is what I have formed in my reaction. You're now going to do that in your lab, and you're going to answer some questions about it. So feel free to pause me. And when you're ready, I'm just going to do one more of these with you. And I'm actually going to skip the first one because it's very similar to what I just did. I'll do this second one, CAS. Okay, so my balanced reaction, I have CAS, and I'm going to break it. I'm going to form calcium, and I'm going to form sulfur. Both of those are actually monoatomic, so I'm already balanced. I'm already all set. This was a +2. This was a -2. This is alone, so it's an atom. It has no charge. This is alone, so it's an atom, and it has no charge. When it was together as an ionic compound, a metal and a nonmetal, there was a plus and a minus. All right, I know that plus is going to get attracted to the minus, and I know the minus is going to get attracted to the plus. My half reaction. So here, the positive is the anode, and this is the cathode. I know oxidation always happens at the anode. So over here, the reaction that happens is with the sulfur. So S minus 2 becomes S by losing electrons. And to balance this out, it's going from a -2 to a 0. So it has to balance out with 2 negatives on this side and 2 negatives on this side. And then reduction always happens at the cathode. So I follow my cathode around, and that's where my calcium is. So Ca +2 plus those same 2 electrons. Literally, these 2 electrons are going to get gained by the cathode, and it's going to form calcium. So this side's going to clump up and gain mass as it forms calcium over here, and this side is going to form sulfur. All right, thanks for joining me.